All right, guys, so our first example was fairly straightforward. This one has a little bit more teeth on it. And so I'm going to go ahead and draw what the diagram looks like for this guy. We have a mass that's being held down by gravity, mg. Mass of the rock times gravity. It's being held in place by a string, and it's creating tension. And it is at an angle with the vertical here, okay? And it's spinning in a circle, and so it's kind of tough to see on a two-dimensional surface here, but there's a circle it's going in right there, so it's going to have a radius r. And I know, because we're really good at trig now, if the length of the string is L, and this is theta, and so this is L sine theta, that is going to be the radius of the circle I'm going to be dealing with. We're going to need that later. So let's go ahead and do Newton's second law. And so let's do the x direction first. We know that there is a centripetal acceleration directed inwards, which means there is a force directed inwards. It looks like the centripetal force is the net force on the object. There always is a net force on the object if it's moving in a circle. So the centripetal force looks like it's equal to the x component of the tension. And so we have the tension going this way. Looks like it's t sine theta. And the tension going this way is t cosine theta. So it looks like the centripetal force is equal to t sine theta. There's that guy there. That's in the x direction. Well, in the y direction, it's not accelerating in the y direction. So that one looks like it's fairly straightforward. It looks like it's t cosine theta. That's going up minus mg equals 0. So that is going on here. So it looks like t cosine theta equals mg. And I'm going to go ahead and solve this for tension. It looks like tension in the cable or the string is mg over cosine theta. I'm going to need this guy here in a little bit. So we've solved for tension. And if I know anything about centripetal force now, it is mv squared over r, right? That is m times centripetal acceleration. Centripetal acceleration is v squared over r. So I have mv squared over r equals t sine theta. And once again, we're actually looking for an expression for the speed which it goes across. So we're going to have to solve for v here. So a lot of this now is going to just start plugging and chugging a little bit. I have mv squared over r equals t, and I'm going to plug in my value that I found over here on the right, mg over cosine theta. So mg over cosine theta is tension times sine theta. So I'm going to use one more little math trick here. Is I'm going to call this tangent right here, these two guys, sine theta and cosine theta. And I'm going to also change my r into the L sine theta. So I have mv squared over L sine theta equals mg tangent theta. I'll finish this off right here. So now it kind of looks like this. Notice my m's cancel. That's good. So I have v squared equals L, length of the string, times g, times tangent theta sine theta. And if we stick that in the calculator, it looks just like it's supposed to. So then I take the square root of this, so v is equal to Lg tangent theta sine theta and take the square root of that. So this is what the expression for the velocity of a rock swinging in a horizontal circle is. Once again, there's lots of math involved once you get past the original expressions for the X and Y directions. Okay, I hope that made sense to you guys. Talk to you later. Bye.